Welcome to all the participants, and I will start by making the presentation of the case of Flores Malacca project. The Flores Malacca project is a mixed building complex. That means you have both residential as well as office mixed together in the whole complex. It is located in a city called Le Port, which is in the northern tip of Réunion Island. Réunion Island is located somewhere between Madagascar and Mauritius. You can see here the southern tip of Africa. Beside that, it's Madagascar, and Réunion is a very small island. It belongs to France and overseas territory of France. And in Réunion, you have a city called Le Port, which is marked as red here, the northwest of the island. And this is where they wanted to start a new project. The building is located in the southern hemisphere. The latitude is about 21 degrees south. Just a few words about the location itself. The project is a large urban development project. As the population increased in the island, they wanted to create new areas. Basically, people had settled in different areas, and the island has coastal parts, but also highlands where it's less populated. But over the years, many people are coming and settling down there. So they had to create more spaces. And one of the plans was to extend the urban zone and create new pockets where they could accommodate more people. So Le Port is located in a place which has highest solar radiation in the island itself, and the trade winds from the southwest side in winter and northeast in summer. The island itself is, has a very good climate in the sense that being surrounded by the sea, the temperature really doesn't go up very high. The maximum temperature we're talking about Le Port has the temperature of about 21 to 29 degrees. And this is on the right-hand side, you can see the monthly variations. The red one shows the maximum, the blue one shows the minimum, and green is the average value. And average you can see is about 21 to 29 degrees. Summer months, January 29. And then it goes down in winter, you can see the temperature can be below 20 degrees because especially at the high altitude, the temperature can go down much below that. You can see the range of 7, the zone 7s, the temperature can be as low as 8 to 15 degrees. These are average values. It can go down to as close to 0 degrees Celsius, particularly near the volcanic area. There is a big volcano which erupts from time to time, and that's at a very high altitude. That's where the temperature can go down to as low as 0 degrees Celsius at times. So Le Port is a location where they have a lot of sun. You can see the sun shines more in this area compared to other places. It's hotter, and at the same time, the temperature in winter can go down to below 20 degrees Celsius. So it's not really very, very hot compared to many other tropical zones. This is showing you the wind pattern of the site. As it was mentioned earlier, you have wind patterns changing. From December to March, there is a particular wind pattern, and from June to September, there is another wind pattern. December to March is the summer period, whereas June to September is more in the winter period. There are certain times when the wind velocity can be pretty high, going above 8 meters per second. And that's why they have to be very careful about designing of buildings to protect from the strong winds or rains during those periods. So the main objective of this project was three-pronged: how to improve the living condition of the people who would stay in these places. I mentioned earlier, people were mostly living in individual houses, not densely populated. But as the population increased, they had to make it more compact, and that changed the lifestyle of people. So one has to make sure that while pushing the people to live on buildings which are more than 1, 2, 3, 4 levels, how do you improve the living condition of the residents there? The other one was to look at how to reduce the emissions. This is the policy of France as such. So being a French overseas territory, they also followed the same regulation of how to minimize the CO2 emissions. And building sector is one of the sectors which contributes heavily to the emissions in France. So they try to see how to minimize the CO2 emission even more compared to the mainland, because in France itself, much of electricity is generated from nuclear power, whereas in this island, they have to depend on fossil fuels to generate electricity in the past. It's a mixture of fossil fuel and hydro, but over the years they're trying to look at how to bring in more of solar, wind, and biomass cogeneration, because there is a lot of sugar plantation. From there they produce bagasse, and bagasse is used for cogeneration, production of heat and power. And the last one was how to meet the ambitious target of having higher share of renewables in their energy mix. So these are the three objectives which are set for the project. The whole building complex was about 9,000 square meters, and it's actually two triangles separated by a road in the center. We have the northern triangle and the southern triangle, covering about 5 building blocks using the bioclimatic principles to minimize the need for energy and improve the comfort. And the idea was to build energy efficient homes, particularly for low income housing, so that people don't need to depend too much on mechanical cooling systems, whether it is fans or air conditioners. So it was right from the beginning designed in such a manner that people would not be using air conditioning neither in homes nor in offices. And there were some few offices and shops in that area, so that there is a neighborhood concept. People don't have to walk very far or drive to other places to get their basic requirements. This is showing you the sun path in different periods of the year, summer, equinox, and winter. In the southern hemisphere, you can see the sun path in summer, where it is, summer means it's going down south. It just crosses because it's at about 20.5 degrees. So the sun path, it goes up to 23 degrees. In summer, the southern facade is exposed to the sun to some extent. Whereas in winter, it is always in the northern hemisphere. And during equinox, it's more or less going overhead. There is, they don't have to worry about the southern facade. So the major challenge for them was to minimize the heat gain from the northern facade as much as possible. And particularly in summer times, southern facade, those areas which are exposed to the sun during the hottest period in the year. In Réunion, just like in France, they have their regulations for constructing buildings that are low energy consuming. Most of the islands that are French islands, which are located in the tropical areas, they have these policies to push people to construct building to minimize the energy use. But in Réunion, they have their own standard they have come up with, which is called PEREN. How do you create more energy efficient buildings by which you can achieve net zero or net energy positive buildings? Keeping that in mind, they have come up with standards, which is known as PEREN in Réunion Island. And the aspects they look into design buildings, particularly for the thermal aspects. How do you make sure that the building is well integrated with the surrounding environment? How do you ensure that your roofs and walls are well protected from the sun? What are the properties of the windows to be used to minimize the heat gain through the windows? How do you make sure that you are protecting them from the sun through sunshades? One aspect which is very important is to promote more cross ventilation, natural ventilation as much as possible, by which you can avoid the need for cooling by fans or air conditioners. The type of fans, more efficient fans to be used. In offices and shops, they promoted fans, mostly ceiling fans, whereas in the homes, only during a certain period, they required those, and they're promoting more the stand fans, which can be moved around depending on the comfort required by the people. And since its location is the tropical climate, the emphasis was more to use the daylight as much as possible during the daytime, natural lighting, so that you minimize the need for artificial lighting. These are the aspects which were mostly looked into. And while designing this building complex, they went through each of them. So we will go through them one by one to see the details. Surrounding environment is very important, because you can see more and more cities, we have the problem of what we call the urban heat island. A building may be designed very well, but all around, if you have asphalted spaces, which are absorbing a lot of heat during the daytime and radiating at night, making it very uncomfortable when the temperature comes down at night, because the radiation effect from the surfaces which have absorbed the heat, you would have a urban heat island effect, and the temperature can go up by 3, 4, 5 degrees, even higher in certain areas. So to avoid that, parent recommendation is to avoid asphalt and concrete surfaces as much as possible to minimize the heat gain and increase the air temperature around the building. The finished flooring from the building should be protected as much as possible from direct sunlight. And the idea is to have as much as 3/4 of the periphery leaving a bandwidth of 3 meters, where you can have more green surfaces instead of hard surfaces. This is the recommendation. We'll see what has been done in the case of Flores Malacca. As I mentioned earlier, there are 2 triangles. Malacca is on the northern part of the road, which is dividing the two, and Flores is on the southern part. And the green areas which are marked showing these are the periphery of the buildings, and the total linear facade is about 257 meters. And as much as 58% is a green facade or protected facade. So, which is more or less meeting the requirements of PEREN. And same thing for Flores. slightly less, 55% of the surrounding are covered by green facades. Certain areas they're not covered, they could not do that, but we'll see what other measures they're taken to protect them from the heat as much as possible. So the effect was to have harmonious integration with the surrounding as much as possible so that there is less heat island effect. The other thing they try to look at is to have a good integration with the surrounding, meeting the district at the district scale to keep a harmony so that you don't see suddenly some buildings popping out like this. So as you went up in the heights, the buildings were receding gradually so that you would see the levels going up as you go up steps on the higher levels. This building was about 5 stories with an underfloor. The vertical layout is integrated with the topography so that according to the slope of the location, they try to build it around it, not by filling up so much of energy. And visual comfort was considered while sizing the windows. So the tendency was to have higher windows to wall ratio at the lower level. And as we went up, the window to wall ratio was reduced gradually at higher levels so that people could have a better circulation of air at lower level where it is required because you have surroundings, and vegetation as much as possible so that you create sort of barriers to provide privacy to people who are living at the lower floors. The next one is to look at thermal properties of the roofs. The parent recommendations are to keep the solar factor as low as 0.02. Solar factor is nothing else but the amount of energy that you receive on the walls during the sunshine hours. What percentage of that is actually being transmitted into the building, interior part of the building. So they're talking about only 2% allowed to go in. The rest is supposed to be blocked so that the building does not gain heat through, this is for the roof, okay, on a rooftop. So they had studied three different types of roofs. The first one is roof terrace garden using greenery, plants, along with concrete slab and waterproofing plus plants. And you could achieve the parent target of 0.02. It was slightly lower than 0.02. The second one is to have accessible terrace roof with an over roof so that you can go to the terrace, but on top of that, you have an over roof by which you create a protection above that. And the over roof, we'll see later, can be used for other purposes like generation of energy, electricity, or hot water. And here, of course, they could manage to reduce it much less than the parent requirement of 0.02. It was about 0.01. The third one was to look at roof terrace with slabs on pedestals, concrete slabs, insulation, waterproofing, and slabs on pedestals. And this was more or less the same result as the type 1. And these are the three that were considered, and they have been used in the buildings to the extent possible so that they can meet the parent standard. When it comes to the opaque walls, the solar factor that is set is not to have more than 0.05. We have seen in the previous slide, we talked about having 0.02 for the roof, because as we know in tropical climate, the sun is overhead most of the time. So the maximum amount of heat gain is from the rooftop, and that's where more efforts are made to reduce the heat gain from the roof. When it comes to the walls, it's 0.05, and they considered 4 different types of walls. Metal cladding in front of the concrete wall. By metal cladding, they use a metal surface which is highly reflecting so that it does not absorb the radiation which is falling. Most of it is reflected, and they could achieve very low value, just like we have seen for the roof, 0.01 with this solution. The other options were fiber cement cladding in front of the concrete wall. And these are the walls which are exposed to outside. We are not talking about the walls which are partition walls inside the building. These are all exposed to the outside. The third one was a concrete wall with insulation. And the last one was a pure concrete wall. You can see here, there is no option for using of brick. In the island, they don't have much facilities to actually construct with brick because they don't have the raw materials necessary and also the firing. And much of the materials that are required in the island are imported from elsewhere. So it's much easier for them to make concrete buildings than to have bricks, because it was not available. In the traditional way, They actually use lots of stones as well as the seashells, which were used as building materials. But over the years, they've shifted to more imported materials for construction of buildings, because the island does not have that much of resources to take care of all the needs of the buildings in terms of construction of buildings. So these are the 4 walls constructed, and I can see all of them actually met the standard of 0.05. They're below 0.05, all the 4 cases. The next one was to look at the openings on the facades, mostly windows. The parent recommendation is to have the solar factor different in different direction depending on the solar position. We have seen the sun is there mostly in the northern side, so that's where they have efforts to bring down to 0.2. But in the southern side, because that's when in summertime the sun is on the south for a short period, and it was important to block it during that time because the ambient temperature is high. On top of it, if you get solar heat, then it will become quite unlivable in those areas. Whereas in the case of winter, the solar factor was considered much higher than the summer, because that time the ambient temperature is actually low, and they want some free heat gains so that people can feel more comfortable. When the temperature goes below 20 degrees or 18 degrees, they want some free heat. And so it was not very important for them to have low solar factor in winter months. And further, the openings which are provided with sunshades, there are more details here. I will not go into all these details. It was basically talking about how far the sunshade should project out compared to the height. For different sizes, they've given some specification of what should be the equivalent solar factors. Now you can see solar factor is higher when your the projection is shorter, only 0.25 compared to when the project is 1. The distance is much more compared to the height, and that's where you can achieve much lower solar factors. This is the parent recommendation. Next, we go to air circulation, because as I mentioned, this was very important for them to have natural ventilation to the extent possible, because being close to the sea, they have the sea breeze coming in, and that brings in fresh air. And the idea was to ensure cross ventilation in all apartments in the different facades, okay, so that you can benefit from the natural ventilation to the extent possible, to have cross ventilation in all the apartments. So for each of the apartment, they looked into the details to see how they could enhance the air circulation as much as possible. Parent recommendation talks about 20% of free opening area compared to the facade area, 20% of opening area to benefit from cross ventilation to the extent possible. These are some of the protections that were utilized depending on the location, from the top, from the sides, the different sides, by which they could create enough shadow to protect the openings from direct sun, whereas allowing for having enough indirect light, diffuse light to provide daylighting during the daytime without bringing in the heat along with it. There's much more to it. My colleague will show some more details of how they could manage to reduce the heat gain through the windows. These are some examples of sunshades, depending on the location, depending on the direction. They used louver porches, shading the external passageways, so that when people walk at lower level, they are protected from the direct sun, to encourage more people to walk around and interact with each other, to improve the mixity as well as the quality of life of people. Horizontal blinds used in certain places. You can see lots of vertical fins as well. These are the areas where they have got trellis screens to protect from the direct sun, whereas people could have their views outside. And over roofs, everywhere you can see on top, there are over roofs. These over roofs are creating a gap in between for the air movements to take place, and the rooftops are used for energy generation. People can make use of these areas. On top of it, they have energy generation facilities by which you have good ventilation movement and there is no heat gain from the rooftop. These are some examples of different apartments having cross ventilation design, depending on the periods of the year. In summer, winter, the orientation was designed, taken care in such a manner that each of the apartments would have possibility of cross ventilation in certain areas at least. The bathroom toilets were kept more outside so that they created a buffer zone, and they were ventilated either naturally, and where it was not possible, they use extraction fans. When it comes to lighting, basically in the island, they have done studies to see that lighting represents about 10% of the total energy consumption. So it's fairly high. What measures they can take to reduce the artificial lighting? So they looked at wherever natural lighting was possible during the daytime to make best use of it. And whenever they went for artificial lighting, to use the most efficient one and use more of what we call task lighting. The lighting should match with the need and not just providing uniform lighting everywhere. Okay, so wherever there is more requirement, they would provide more lighting. And lighting which is not suitable were eliminated during the designing stage itself. Cooling strategies, keeping in mind that they wanted to have net zero energy buildings or very low energy buildings. They decided right from the beginning, these buildings will not depend on air conditioning. As we have seen, the temperatures really don't go up beyond 28, 29 degrees in the summer months. So there is not a need for air conditioning as long as you can protect the building from the direct heat gain from the sun, and you can provide opportunity for the heat to be evacuated from inside by having cross ventilation when the outdoor conditions are favorable. So to keep track of that, they try to create evapotranspiration by having native vegetation around the building to the extent possible. You can see in certain areas, they also have rooftop facilities at different levels. And as you go up in the heights, you can see there are receding areas so that it's not just one flat facade, it is changing with as you go up in the height. A lot of wooden claddings used. Wood is a material which is renewable. To the extent possible, they have used as a material, wood as a material, and having louvers inside, of course, wherever there were windows, the louvers were designed with glass, and they were well sealed because of the strong wind. They had to protect from the wind as well as from the rain. Only the offices and shops were equipped with fans. The rooms, the homes were not using fans so much. But during summer months, if people required it, there's a provision for them to borrow the fans. These are the table fans where they can move around in the area they require it. It was not big blocks. They were separated out in different areas, fragmented in a manner so that they would allow for the air to move. I will show you some photos of the buildings later on so that they can appreciate how it was designed to allow the air movement more easily around the buildings, and limited use of mechanical systems. I mentioned in toilet and bathroom, first priority was to use natural ventilation to the extent possible. When it was not possible, to use mechanical ventilation, extraction fans, which are mostly on the facade. For renewable energy system, they made best use of it on the rooftop. As I mentioned about the over roof, the over roof was designed in such a manner that on top of it, they use solar photovoltaic panels as well as solar water heaters, by which they could meet their hot water requirement. You've seen in winter, the temperature goes down, people do require hot water. So they have hot water facility as well as electricity that is required for the buildings. Much of it comes from the solar electric power plant, which is on top of the roof. And the other advantage is, as we know, photovoltaic panels, as they're exposed to the sun, as the ambient temperature goes up and the sun hits the solar panels, the solar panel temperature also rises. And according to the principle of electricity generation from photovoltaics, higher the temperature of the surface, lower will be the output. By having space in between, they could allow the air circulation between the roof and the roof of the building, and it would take away the heat from the panels. And at a low temperature, the panel performance was much better. This is the finished products you can see on rooftop. There are solar panels, also solar water heaters. The water heaters are on the rooftop, but they're all connected to reservoirs or tanks which are in the apartments, so that it's not centralized in one place. The hot water which is generated is provided to these tanks in the different apartments. And in case the sun is not available, the apartment that require hot water during certain time can have their own backup system, by which you minimize the heating of big quantity of water. Whoever requires it would only utilize it as a backup supply for hot water in case the solar availability is low in winter months. Annual energy consumption, you can see average is about 28 to 40 kilowatt hour per meter square per year. In France, low energy buildings, that is in the mainland France, which is more in temperate climate, the low energy buildings have by standard, they should be below 50 kilowatt hour per meter square per year. Here it was about 28 to 40 kilowatt hour per meter square per year. Some of the architectural features were to promote more social integration. In the islands, people tend to have more interactions among themselves. There are lots of festivals. People come from different areas. There are local people. There are people coming from France, people coming from other parts of the world who have settled over a period of time. And they have lots of festivals throughout the year where people interact with each other. And living in lower levels, they have more chances to meet. So the idea was to maintain the same social integration to the extent possible. One of the things that we have seen, the houses are not only for the families, but also for the students. About 1/5 to 1/4 of apartments were meant for students' accommodation, so that there is more interaction between the students as well as for the families who live together. So they were not isolated, which is normally the case for many hostels for students in the cities. One of the things that they look at is not to have a separate building entrance. Okay, everybody comes together. There's no building entrance for students separately. There's no building entrance for the offices separately or shops separately. They mixed in such a manner so that there is no social hierarchy. People come in from any areas. There is more mixity between the people. And the pathways were broken in such a manner that they would have space for people to meet and interact. Lots of detached walkways. In the photo, you can see these are the passages which are shaded so that people can walk around and meet and talk. But they're always away from the houses. They're not attached close to the houses so that there is no noise pollution. And there is also privacy for people who are living there. This was in the beginning where the plants were small. Later on, the plants have grown to become much bigger to create a sort of a barrier between the place where people move around. So even from the top level, upper levels, the passages for people to move to their apartments were separated from the building itself, with the idea that when people move around here, they're not disturbing the dwellers here, and people here can keep their doors, windows open to have more cross ventilation because they're not intimidated by people who are working in the passages. Some pictures of the building once it was completed in 2011. You can see, depending on the location, here you can see very well how the openings are well protected from the sun overhangs. In other areas where directly exposed, you can see in those cases they have vertical fins which are provided. On top, they also have trellises here so that it keeps the rooftop cooler. These are penthouses on top, and they're all covered with solar panels or solar water heaters in different areas. They're separated, you can see, by the road. They try to minimize the hard surfaces to the extent possible. Also create areas for recreation of people so that people can come out and spend time together, chat. And you can see very little space for parking of vehicles. There are some areas here on the right, here for people to offload their, for example, if they go out for shopping, bringing heavier things, they can keep their car for a short time and unload, offload their shopping materials and then move on. Much of the areas in the island, they try to see how to create the parking in the underground so that the upper portion is left to have more green space and to create a natural environment to the extent possible. This is another angle. I mentioned about the space left between the buildings so that you can have good natural ventilation, cross ventilation, also privacy of people in the different buildings. This is an example I mentioned. Here in the center, you have this staircases being only 4 or 5 stories. They don't encourage lifts to the extent possible, elevators to the extent possible. And these are detached from the building so that when people carry out the movement here, there's no disturbances. And when people move from one floor to another, there is privacy for others to maintain so that they can keep their doors, windows open without feeling the presence of people around them. The shading, you can see here, there are vertical shading, there are horizontal shading, depending on the orientation requirement. They provided different facilities. These are mostly for the toilets, exhaust for the toilets, natural ventilation. In some cases where the natural ventilation is not enough, they've used exhaust fans to the extent possible. Again, these photos were taken in the initial phase. Over the years, many more trees have come up. This is an example of, you can see the part which is exposed, but at the same time protected from direct sun, whereas it allows for the wind movement to take place through these louvers. These are all wooden features. And this is actually your staircase area and people to move around from one end to the other end, which are detached from the building, so that they just, wherever they want to go to the apartments, there is a passageway that they can take to go to the rooms at different levels. Other examples of how we can see the sun shading is very, very important wherever it's possible. I don't remember if I showed you somewhere the facade where they have metal surface. This is metal cladding, you can see here. This is a special type of metal which reflects most of the solar radiation falling on it, so that the wall behind hardly gets any amount of heat coming in. This is a very effective way for them to protect some of the areas by blocking from the sun the whole wall, particularly the areas that are more exposed, because at a higher level, they're not able to provide that type of shading with trees, etc. This is an example of, this is a photo taken in the evening hours, and you can see the sky can be very cloudy and rainy at times. This is near the coast, but you can see within 10-15 minutes time, they go up to very high altitudes, the mountains, and the areas there are much cooler compared to the flat areas. And that's why they said these are the hottest areas which are closer to the sea, but they also have the advantage of having the sea breeze coming in later part in the day. Some more areas, they try to create as much green space as possible by having plants in between. And these plants are exposed directly to the sun on top, whereas they create a barrier between the staircase and the people living there. You can see a lower level, lots of green surfaces, lots of areas where people can sit and chat, meet each other without disturbing the people living in those buildings. These are, again, initial phase of the trees have just been planted. Over the years, the whole area has changed quite a lot. Some other facades of the building. So with this, you can get some ideas about how they could design buildings in an area where they could achieve almost low energy, and with the solar facility, they could achieve net zero energy buildings by providing good protection, having natural ventilation to the extent possible, avoiding air conditioning, and providing fans when it was an absolute necessity. So with this, I will stop my presentation. I don't know if there have been some comments or questions in between, because I have not seen any, or there are several of them. I hope my colleagues have answered some of the questions that you have raised. Yes, I do see my...
Yes, Brahma.
Yes, I see that my colleagues have done a very good job to respond to... Yes, that's CK, my colleague.
Yep, hi. Hi, Dr. Monty. I think one of the most interesting questions we have on the chat box is regarding the insulation of the wall, wall solar factor. If you don't mind, return to that slide. It's very interesting numbers.
Okay,
a few of them highlighted those numbers. It seems that the insulated wall has higher solar factor than the conventional concrete wall, an insulated concrete wall.
Let me just get to that. This is the one you're talking about?
Correct. Yes. This is the one. Yeah.
Yes.
The lowest solar factor is a metal cladding in front of the concrete wall. You show us that.
Yes.
Yes, a white painted surface to reflect most of the heat away.
Yes. You are saying why it is concrete wall plus insulation has higher solar factor compared to concrete wall, right?
Yes.
Yeah, that's because I have not gone into the details of the composition of the concrete wall.
Okay.
So because the concrete wall thicknesses are different and compositions are different, and because of the shortage of time, I have not gone into the details of the different composition. Okay. I could have, if those who are interested, we can share the details of these 4 cases. There was much more detailed information available. I could not compress it within half an hour's time. Yeah, so I've not given the details. So you can understand why. why it is with insulation, it's higher than the other one.
Yeah, it does appear that even type 2 with the fiber cement cladding is also higher. So the only one that actually works very well is the metal cladding. And as you have presented earlier, is actually painted white, very highly solar reflective.
Yes, the metal cladding. And that is why in the island, you can see many places they're using this metal cladding to really cool the surfaces, particularly the ones which are exposed to the sun in summer months.
Yep.
Okay? So it's very selectively used, not everywhere, particularly the ones which are exposed to the sun in summer months.
A little bit related to this, there's another question about the use of thermal mass in this climate.
You can comment on that, perhaps.
Okay. Well, looking at these numbers here, I would say that the thermal mass actually works quite well in a way, because the metal cladding with the concrete wall have the lowest. It means that the concrete behind the metal cladding is actually storing the cooling from the night before and keep it cooler throughout the day. That's how I look at this. But we really need to study the simulation data to confirm if this is the case. But you see in type 3, in a concrete wall with insulation, normally such wall are insulated. The insulation is normally on the inside because they normally want to protect it from the sun and rain. And once you insulate it on the inside, the thermal mass is not occurring inside the building. It's actually occurring outside. So it looks like a thermal mass actually from one glance in this data, I would say thermal mass actually works in this climate.
Yeah, Brahms, if I can jump in and come in.
Please do.
Yeah, so some very interesting questions has cropped up regarding to the cladding, the facade materials, the walls. One interesting to me is albedo. I think taking on the larger picture of urban heat island and how can these facades and the albedo or the color, the absorptivity and the emissivity of the materials used for these building envelopes, how they can help with the big picture. I think there are several questions related to that, and also this question that CK just tackled. In this sense, we expect high albedo materials in the urban context to help overall with the urban heat island scenario. That means how fast the urban context cool in the night time. And so that has become quite a pressing problem for us, where the urban contexts don't cool as fast as the rural areas or the less built areas. So that is something that we like to see happening. And so there was a question in terms of whether the reflection or the solar reflected index would matter to the outside area. Yes, we must take care when we are dealing with, say, white walls and the glare that it will cause us for the neighbors, etc. But if used with concern or with proper thinking, it can be a huge advantage for energy use. In the context also, we can see that albedo, sometimes it might have effect for not our area or the areas most adjacent, but down plume. That means in terms of urban heat island areas beyond our. So it is sometimes linked to less rainfall, etc. But in the immediate context, it can be very, very advantageous in terms of energy and urban heat island reduction, the overall picture. So
thank you.
Just like to mention that.
Thank you. You can see, to support what you said, Naren, you can see here the cladding. So it's not something which hurts the eyes of people who are walking by. You can see the surface is done in such a manner that it's not directly reflecting on, for people who are walking. It is ondulated. Can you see the detail here, Naren?
Yep.
Yes.
So it is designed in such a manner that it will reflect the solar radiation to the extent possible. But at the same time, it does not create a sort of glare for people who are walking by. This is something that we find in many cities nowadays. The glass surfaces, reflect so much that people can't look up.
Yeah.
This is not something that you feel. I have been to this place, so I know there's no problem as such. Even in the peak summer days, you don't really feel that much of reflection coming from there, hurting people's eyes. Any other questions that you have not covered so far?
Okay. There is one question about the AAC world. They asked whether we can change the metal cladding and the air gap with inside the concrete wall by AAC. AAC brick is very common in, I think, yes, in Vietnam and in Singapore and as well as Malaysia.
Yes.
And it's often used for the air conditioning apartment. Yes.
Good question. We are not promoting that whatever has been done in this project should be done everywhere else in the same manner. We have to look at local materials, what is available and which is effective. So in this particular island context, because everything they're importing, so they have a choice to import certain things which are more effective than the others. So it cannot be generalized for all cases. Wherever the local material is available, you mentioned too about Vietnam. In Vietnam, for instance, you are using more the fly ash from power plants, which are mixed to increase the volume. At the same time, the government now has a regulation to go more for compressed earth blocks, yes, to the extent possible in buildings, because they have realized that fired bricks are causing a lot of deforestation in various parts of Vietnam. So it's very specific to the local conditions. So we are not, through this example, our objective was not to promote any particular type of materials, etc. We are looking at how to minimize the heat gain. What are the different solutions possible? Okay. Here, obviously, they're using wood, which is again sourced from locations where there is no deforestation. And a lot of it is used, a lot of wood is used in these buildings because it's for them it is renewable. The sourcing is very important. If you're just cutting forest and putting wood, it doesn't make sense. So by all means, please do not take this as something that we need to copy everywhere. We are looking at the different aspects. What are the aspects to be taken into consideration to minimize the heat gain? And what are the aspects to be taken into consideration, particularly for natural ventilation and cross ventilation in tropical areas? Something that I didn't mention, in Reunion Island, they have been working a lot because the objective is to avoid the new constructions using air conditioning, because the normal trend is now air conditioners are available at such cheap rates. The normal tendency is to just buy air conditioners to be comfortable. So there is a conscious efforts to look at how to design buildings and convince people that you don't have to spend more money, because when you're investing on air conditioning, your running costs are also high. And they have been doing a lot of modeling, not just using the computer software, but they also do what they call wind tunnel modeling, physical modeling to see how effective the solutions will be using models, real scale models. And these are done in a laboratory called Eiffel Laboratory. Eiffel is the engineer who has designed Eiffel Tower. And he has done lots of structural designs. And in his name, there is a famous laboratory in Paris where they carry out this modeling of various type of projects to see the impact. At present, a lot of the projects are mostly for studying the movement of vehicles at high speed. What happens, for example, if the vehicle is moving at high speed, you have snow all around, what happens to that? So since the laboratory is available, the facilities are available, the scientists and builders of the island are using more and more this facility of the laboratory to test it out, to see how they can achieve as much as possible cross ventilation in a good manner and avoid the effect of overheating. Two good examples I can cite are, one of them is the amphitheater of the university, which was constructed not so long time back for 550 students. You could accommodate 550 students. And the whole amphitheater is designed in such a manner that there is no air conditioning. It is by design to extract all the heat through mechanical means and natural ventilations, etc. So it is possible again by modeling the real case to see how effective it is. The other one is the extension of the airport that they're doing. The new airport is going to be fully non-air conditioned. So they're also doing the testing of in the laboratory to make sure that they don't do mistake, because once it's done, then there'll be a lot of criticism saying that you did not achieve it. You have to go back to air conditioned systems. So wherever it's possible, people are starting to look at physical models to make sure that things work and not just on computer simulations.
Okay, Dr. Manti, I think we have 3 quick questions, and then I think we can move on to 2.
All right, you can perhaps read out and see if you can answer
the first quick question is, do they use lighting sensor to turn off the lights or reduce the lighting level? And the use of LED lights, are they used in this project?
Okay, the lighting is, of course, always they look at efficient lighting. And in the residential areas, the homes, they don't have any sensors as such, but all outdoor lights that they have, all the outdoor lights they have with sensors. And the sensors, you can see here in this particular, I can show you here. This is the point where my arrow is, that is showing the sensor. So the sensor senses the lighting and then the lights will come on automatically. So all the public areas, they have sensors and they're very sensitive. The sensors have to be good quality so that they can sense the movement of people and from certain distance, so that people will never feel that they're walking into a darkness. The moment you open your door, the lights come on automatically. So you don't feel that time lag that you are in the dark. So choosing sensors of good quality is very important so that people don't get dissuaded to use this type of sensors to minimize the energy use. All of us know that, particularly the corridors, the outdoor lights, we may require them only for about 5% of the time, whole night. But very often we keep them on throughout the night. And that's a lot of waste of energy. So just by putting sensor, you can minimize the energy use to a great extent, particularly knowing fully well that they're using solar panels to produce this electricity, which are mostly during the daytime. So nighttime, if you can minimize the energy requirement, so you can match your requirement with the generation of energy during the daytime.
Yeah, Dr. Manti, just to be clear, at nighttime, the lighting is actually reduced, dim it down, right? They don't really turn it off. Do they turn it off?
They have 2 types of lighting in some places. They have some low-level lighting where, for example, they have exit lights where you can see it's lit all the time.
Okay.
And when people walk in, other lights come on. Street lights, of course, in Reunion Island, more and more street lights have sensors so that when there are movements, the lights will come on. When there is less movement, automatically the light level is dimmed to a very low level.
Next question. Would the solar PV that tilts towards the direct sunlight gets a higher output?
Sorry, you can repeat the question, please?
Would the solar PV, photovoltaic, that tilts towards direct sunlight gets a higher output?
Well, the whole idea is, the more area which is exposed, the more light is converted into electricity. Yeah. So what if the angle is not correct, for example, if your angle is very low, automatically from the sun, you get much less amount of the same radiation is spread over a bigger area. So automatically your output is going to reduce.
Let me correct the question. Actually, rotating solar photovoltaic that tilts towards direct sunlight, so it follows the sun movement.
You mean the tracking?
Tracking, system? Yes, tracking.
So obviously, the tracking systems do increase the output by as much as 20-25%. Even some people claim higher than that. But the problem with tracking system is you're near the sea, they're exposed at a high level, they have strong winds. So it's not always feasible for them. And moreover, the solar panels costs are coming down so much and they have the area. So in this case, they didn't really have to go for tracking system. And this was done in somewhere around 2008-9. The tracking system was not that popular that time. But in future, people are starting to look at tracking options wherever it is feasible.
Final question is, how about rainwater harvesting?
Yes, that's something that I have not talked about, but you can see here in this particular photo, you can see how carefully all the rainwater is collected. You can see here the passages. They don't allow the rainwater just to fall anywhere. It is all collected, taken to areas. So they do rainwater harvesting in most of the buildings. That's part of their building standards. They try to optimize the use of water and harvest the rainwater as much as possible so that they depend less on taking water from the ground sources. Being in an island, they try to see how to make best use of the water that they get from the rain.
Okay, I think that's it.
All right, so since we are, perhaps I can ask now, I will pass on. Now you can go ahead and do it yourself. This is about the exercise that was given to you. Yes, now we can see it.
Okay.
And I present the case study, the exercise we just given to you. Based on our data, available data we have, and based on some simple tool we just introduced through the MOOC. We here give you like 4 exercise. The exercise 1, we ask you download the weather data of Leopard in La Réunion from the Ladybug website and using climate consultant software to discuss about the master, to analyze the weather data, and after that you can discuss about the master plan design for the project, define some design strategy that you can apply in the building, and imagine where you can put the main function and auxiliary functions like staircase, core, store, and vegetation. So based on the weather data, when you input in the climate consumption, you can see like in La Réunion, the 3 first months of the year from January to March is the hottest, almost the hottest month during years, and sometime during years from May to August, the temperature is lower and even can aim to 15 degrees. The direct sunlight is more than the diffuse sunlight, maybe because it's very close to the ocean. And you can jump to psychrometric chart, and you can see they give you success, use some design strategy. We can see that the comfort zone in La Réunion can get like in 16.6% of the time during years. And using sun setting for the window, you can increase the comfort zone to more than 32.3% during years. So that you can see in our case study, the design, the architect designs already include a lot of shading device in all the whole facade and for the own windows. The natural ventilation also can increase a lot of time during years, more than 50 and almost 60% of time during the years, because here the wind is coming from many directions and they have cooler wind. Also, if using fan, you can increase the comfort zone to more than 3,000 hours per year. So this also explains why La Réunion has a very, very interesting regulation that you need to install 1 ceiling fan for every 10 square meter, especially for public space and public building. This one is already explained by Dr. Mohanty, so I don't talk again. So after analyze the weather data by using climate consultant, you also can using the website we already give to you in the exercise of the module 1. So you don't need to install climate consultant, and you also can use the weather tool to see the sun diagram and so on. So if you look at clearly of the site plan, you can see the architecture design try to put the building set and orientation of the building to optimize the natural ventilation from northeast, northwest, southeast of the site, and especially during the hottest season. The building width of this building is also quite narrow, not so much to optimize natural ventilation. The main design strategy to get the natural ventilation and reduce the energy use, like apply the building orientation, building shape, and setting device, natural ventilation, and apply some fan in some place. I don't know, any of you already imagine where to put the auxiliary functions and the main function in the building. But we can see in the floor plan, the architect already planned to put the staircase and the staircase, the core, and everything in the west and east of the facade, west and east facade. For more clear about site plan, you can look back the previous presentation by Dr. Mohanty. In the exercise 2, we ask you to figure below the location of 5 to figure we show you the location of 5 apartments in the buildings, and we think and discuss about the prevailing wind and how to apply natural cross ventilation in the apartments. The massive and orientation of buildings are applied. Like orientation of building is already applied from the site plan. The position of opening is considered, and the cross ventilation is applied here. They open in one side, the inlet in one side, and the outlet is another side. The size of opening is also be considered, and open type was considered by the architecture design team. They have the door closed, like you can see in the image here. And for the windows, they using the louver. The louver can increase the wind velocity passing through the window. Unfortunately, we don't have the CFD simulation given by the architecture design team and the simulation team, but we can see they put the indoor, the inlet and outlet window, and in both sides of the apartment here. For each building, we have 2 different inlet and outlet. For the exercise 3, before we give you the exercise, we introduce a bit about the design simulation, the building simulation design. The design team using the design builder software to study the impact of wood solar protection using overhang. And here we have 2 different case study consider the solar protection. For the apartment number 3, the scenario 1, the compositions of warm roof, joinery, solar protection comply with the island standard. The roofs of building are solid and heat exchange between the roof and the buildings are neglected. In this case, the thermal insulation of wall and roof is better than the scenario 2. In the same scenario 2, the architecture of the building is identified as scenario 1. However, the composition of walls and solar protection is modified to comply with the future thermal regulation of the island. The wall with the concrete and plasterboard. The concrete with thermal resistance is 0.09, with the thickness is 0.16. With outside plaster, inside is plasterboard. With solar absorptance is 0.04. Solar factor is almost 0.09. The roof are made of concrete insulated on the outside with expanded polystyrene. The roof are not shaded with the thermal resistance is 1, with inside plasterboard with the solar factor is 0.02. The sunset, although here we consider for the scenario 1 as the scenario 2 is all openings are protected by sunset, extending to 30 centimeters, allowing to obtain the solar factor. Fs is 0.65. The pergola overhang the northeast facade of the tower is removed. So we can see the results. So in the image, for the scenario 1 is using less energy for the air conditioning, about 22% reduction when compared with the scenario 2. So the mission we give to you is you can imagine and plan to provide overhangs in the different facades of the apartment number 3, and you can play with the overhang calculation in the link we give on the website, and discuss how and where you can put the overhangs on the facade. Here we just give you an example that we put the overhang in the north facade. The first example, we put the overhang with 300 millimeter, and the second one we put the overhang with the length is 650 as the architecture design team did it at the moment. And we can see the results so that from January to March, during the hottest season, we can cover all the direct sunlight during years. So you can apply easily this tool to any of your designs in the future. And this one is very simple tool and very effective. In the exercise 4, we ask you assume that apartment 3 is an individual apartment, and imagine it at your location. And you can play with the S-Tool software S-Tool to assess the improvement in energy use for apartment by making the following changes. The proposed case, the WWR is 40%. The solar array effectivity for the roof is 0.9. The annual average shading factor is 0.6. The U-value of world is 0.672. The energy saving light bulb internal space is with LEDs around 4 watts per square meter using LEDs light. The COP of FBIC is 3.6. And here an example, we assume the location in Bangkok. And the base case of Bangkok, everything is better than proposed case. Except the window to wall ratio is WWR is 30%, is lower than both case which we give to you. So the result shows although the energy saving is at 36.42%, but the payback time is almost 42 years. So it's quite a lot. Why? So that's the reason why I explained to you that the window wall ratio is 40% is lesser than base case. Because the incremental cost for the window is quite a lot. So you can see on the table to show that although the energy saving for the first, if we apply the only window wall ratio here, the energy saving even cannot set anything and increase. But until at the end, if we of the sense of this sensitivity analysis, it can show the payback time is almost 42 years, although the energy savings is quite a lot. So we should check with another case study. If we reduce the window to wall ratios to 28%, is lower than the base case study. The payback time is 0, but energy saving, you still can have some energy saving, like almost 2%. And for the second case, we apply two solutions, WWR and the solar reflective. We can see the payback time is still 0, and we have more energy saving is 6.3. And we apply the with window wall ratio, WWR and solar reflectivity, and we apply the annual average saving factors. We already have the energy savings is more than 20% and can get the S certificate with the payback time is only 2.51 years. So you can see it's very useful tool. The last one here we show you if we apply individual solution, we can have different results, and we can see like we can see if we reduce the window wall ratio and we apply solar reflectivity, the payback time is none, and you still can have some energy saving because it might reduce the cooling capacity of the HVAC system. So that's why the incremental cost is reduced. Yes, that's all of my presentation. Thank you. Dr. Mohanty, do you want to add anything?
This is a good example to show that parametric studies help us to see to what extent it is possible for us to adopt certain solutions without having to increase the cost too much. And very often when you look at buildings, something that we find that most of the buildings that are designed are already costing us more than the well-designed buildings.
So I should stop share my screen.
No, keep it there so that I can see. Next slide, if you can go down. Yeah. So you can see here, if your window to wall ratio was 40%, you would be incurring higher cost. And this could be in many buildings. We are talking about window to wall ratio of 40%. We have buildings where the window to wall ratio is 100%, fully glazed surfaces. So in those buildings, you can see the cost is already very high. Whereas the moment you are reducing the window to wall ratio, let's say from 40% to 25%, you can see there is no cost, additional cost. In fact, you have a negative incremental cost. That means you are saving money when you go for lower window to wall ratio. Of course, keeping in mind that you don't make it so small that there is no daylighting. There's no natural lighting coming in. So if you reduce your window to wall ratio from 40 to 25%, your cost is not increased, but in fact, it's a negative cost. And negative cost is mostly because this is an air-conditioned building. When you put window to wall ratio less heat is coming in, and your air conditioner size itself is reduced, and you save money, a capital investment in terms of the investment that you make for air conditioners, apart from the energy saving and the cost saving over its lifetime. Okay? So the idea is how far we can actually design things to achieve, let's say, almost 0%. That means there is no overcost. So in this particular case, you can see when we go to these are individual ones. Can you show the combined ones? These are individual ones, right? So here you can see it's a very good example by reducing the window to wall ratio, by improving the albedo of roof, by having better solar reflectivity, and by having annual average shading factor. We have adopted the three of them. Our incremental cost is hardly anything because the payback period is only 2.5 years. Okay, so the incremental cost that you have put in, we can recover within 2.5 years, and we have already achieved 21% of savings. So imagine if all buildings adopted some of these measures in this manner, you can reduce your energy consumption considerably. In edge, if we achieve 20%, that means you have made that target. Okay, and if you are smart enough to go further, then you can make more efforts. But as we can see, it's just like churning milk to get the butter out of it. Initially, when you churn the milk, you can get the butter more easily. And you want to get more, you have to make much more efforts to get more butter out of it. So initial stage, very little efforts, practically no cost, you can achieve 21%. To go from 21% saving to 27% saving, you can see the payback period is increasing from 2.5 years to 8.88 years. And in this one, so perhaps you can see here, if it is 8.88 years and it's coming down to 8.31 years, we should prioritize the light bulbs first before we look at U value of the walls. So it's a must to go for light bulbs in the beginning because your savings can be increased easily without really increasing the investment required for the project, and you can get much higher savings. So these type of studies will help us to prioritize things and see where we can do designing in the beginning and get much savings. And fortunately, now we have new measures. At the international level, there are many countries which have credit lines from the green credits, particularly from industrialized countries. They have created climate credits, and developing countries can tap these climate credits to cover the additional costs. So the new houses that are being constructed, if there is a national movement taking place, at the national level, you can design many buildings and you can get credit lines over a long period of time at very low interest rate to cover these costs. In one of those videos, we had talked about this type of credit lines available through various international development banks like KfW in Germany and AFD from France, the French Development Agency. So that's something that we can also look at. Wherever there is a big interest, we can tap this type of climate funding to cover the additional cost, as long as it is reasonable, within 3 to 5%, and the payback period is, let's say, not more than 5 to 8 years, because the building life is minimum 40 to 50 years, if not longer. So in that, if your initial investment is recovered within 5 to 8 years, it makes sense. And even for that 5 to 8 years, you can get climate credit so that people don't have to put in their own money to get this type of benefits. So perhaps you can stop your presentation, then we can come back to further discussion if there are any questions. Are there any specific comments, questions, or we have covered most of them? I see in the group, some of you are practicing architects. I'm just looking at who are, we have Mona, Dr. Pringle. Would you like to say a few words? Because we know that you have been working on projects where you use low energy materials, low embodied energy materials, not only in terms of energy, operating energy, but also the embodied energy of the building. Perhaps you can say a few words about some of the projects that you have done, share with others.
Thanks for giving me this opportunity, Pramanand. It's been quite interesting how we have structured this program. Actually, I subscribe to it to see how, I know you're doing things very well. So I think it's amazing how you've managed in 5 minutes to give these clips. And yesterday I took the first test, the quiz, and I got, I hadn't seen all the videos and I still got 3 wrong answers. So I'm still trying to figure out. But on the whole, yeah, I think it's a great course that you've put together. Regarding my work, I would like to say that, yeah, we are very privileged to be here in South India, in Auroville, and my practice is mainly based here. I've learned in 30 years to work mainly with local building materials, local craftsmen, and of course with the climate. And I was fortunate to be in a 5-year Indo-US project where I was doing also research on energy efficiency, and where I learned a lot, also where Brahmanand was advising me a lot. It was my first project where I actually worked with data and sensors and did post-evaluation, post-occupancy evaluation, and Golconda was one of them. So yeah, most of our work is,
Mona, just,
a lot of it is vaulting with bricks, with mud bricks.
Just 1 second, the building that you see behind me,
I see.
That is the Golconda building. And, in our, apart from the video, we have reference documents, and you'll find Mona's article there, which gives you much more details. I just wanted to add that. Please continue.
And what?
Your article is available there for people to read through, because apart from the video, there are reference materials. And one of the reference materials is your article, so that people can go through more details, the measurements that you have done, your main findings that we have summarized in the video. Please go ahead.
Yes. Yeah. So yeah, that was part of the work. And I would like to say that the most amazing thing for me when I discovered with Golconda was the landscaping strategy. I never realized that as architects, we work with a lot of the, we knew a lot about how passive design and different materials can help, and how Golconda has dealt with it so well, especially the doubly ventilated roof. But I never realized how good the landscaping strategy works there. So I would encourage those who haven't seen that video or the paper to read it. Because we also, in my work, we do landscaping, interiors, and architecture together, because I feel then it is a holistic concept and it helps us to get everything together at the same time, which we also see in the work that you just presented. Like, unless you deal with what is the surroundings and how the building actually sits in the surrounding, it's not going to, it has a better effect. So yeah, I can go on. But I think that's enough if people want to see my work.
Tell us a little bit about your work with the alternative materials, particularly embodied energy.
Okay, so well, I've experimented a lot with different materials, starting with mud bricks and with CSCB, which is compressed stabilized earth blocks, which are made all locally here, and then of course bricks, which are also low fired, which are just made in country bricks basically, so they're not very high energy intensive. And in my research, I also found something that is very interesting is to when you do a combination of composite walls, like I think somebody was mentioning about in Malaysia about AAC, like ACC blocks, like Aerocon blocks, aerated cement blocks. Those combined with earth blocks in a composite wall section has had a very good effect, as I measured in one of the buildings in Norwell. We also use a lot of stone, like we try to avoid anything that is very highly manufactured in factories, or which is very far away. So whatever is locally available here is so we've done. You can see the wall behind. This is done in lime. This is my studio. I'm also sitting in a vaulted ceiling. Unfortunately, can't show you all. The light is gone, but yeah, you can see some of it. Well, not so much. But this lime wall was a very nice experience because we actually bought the lime. We bought the shell limes, and we slaked it on the site for a few months. Like the older, the better. We had about 6 months. And then I experimented with trying to do different samples, which did not use very, because the recipe is quite secret. The old traditional recipe, we don't generally get all parts of it. So I said, let's not try to just make it very simple that anybody can use it. So I just tried with very simple methods, like with a little bit of white cement, with a little bit of marble powder. And it's really very effective. I mean, it's very simple to do. And I can improve upon it. There are a few small cracks, hairline cracks, and I think I didn't use enough marble powder in it. But it makes a big difference in terms of the temperature. The hygroscopicity of the lime is very good. Yeah, and that's majorly, I would say. I don't remember other things at the moment, but
Thank you.
Yeah, we do work a lot with building biology, which is very a big part of the project of our work, building biology. So it deals with buildings as a third skin. So it adds one more dimension to the work. So we try to make buildings that are healthy, also considering electromagnetic fields. But that's a whole different chapter. Yeah. Thanks, Ramanand.
Thank you, Mona. I see that we have architect Tanvi there. I know that you have tried to answer you have done the exercise for the Flores Malacca project. We did not comment on it because we wanted to keep it for discussion during this session. Tanvi, if you are still there, can you just switch on and perhaps share your thoughts? Very nice of you to have attempted that exercise.
Oh, thank you so much. I should actually thank you for putting up such a great course for us. And it was really good to actually brainstorm yourself into thinking that any strategy can work at different places. Like when I think it in terms of Pune, few things do change, like the wind velocity or the wind direction, and what all different things can you incorporate into the building as in case of design intervention. It does make us as an architect think that there are so many different options that we can work on. So it was really helpful for that.
Thank you very much. And thank you for very actively participating in the discussion forum. Quite a few of you have actually spent your time to go through the discussion forum. And we believe that apart from the videos and the materials, one can learn a lot by just exchanging in the discussion forum, because it's not between the trainers and the participants, but also amongst the participants. Most of you are professionals working already in the field, and you have a lot more to share with us.
Right. So, and in module 1 and module 2, we could like discuss on various cities, like some were from Chennai, from Indore, Lucknow, Jaipur. So sitting in Pune itself, I could understand various strategies what are used across India or even across the border. So it was good to go through such discussions.
Yes, and you realize that you can't just bring any type of building, put it anywhere. You just have to first think about the climate, the local conditions.
True. Yes, sir. Yes, sir.
Thank you very much for your active participation. Not only you, and there are many others. And we hope if you have not been through these discussion sessions, they are still available to you till the 28th of May. Do go through them, not only what you have responded and the type of feedback you have received from us, but also what the others have said. Many of them are very, very interesting. And we have learned from you when you shared your thoughts that we haven't thought about in our discussion in preparing our videos. Okay? And we hope we can do it better in next sessions. Is there anybody else who would like to, amongst the participants, would like to say something, share your views? Maybe I would like to invite my colleagues, Ms. Tu, CK, Naren, Dr. Alfata, Dr. Raula Atalage, if you can say a few words before we wind up. And just keep in mind that do give your feedback. It's not a very long one. In the MOOC, at the end, we expect you to give some feedback. This is mainly to help us to do better. I have already mentioned twice that we are looking at how to come up with the next MOOC, which is more about natural ventilation, cross ventilation, because there are lots of sciences in that, science as well as art in that. And our colleagues, those who are not present here with us, particularly from Reunion Island, they have worked a lot in that. So with them, we are preparing the next MOOC. We are thinking of preparing the next MOOC, which will be more about ventilation, cross ventilation, and the impact of the surrounding. That's very important, as we have shown in this particular example. So you can expect us to have more of these MOOCs. And depending on your feedback, we can try to modulate them and take your suggestions into account to make things better. Sometimes we have not been very effective in the sense that this was the first time we were doing a MOOC. So there were some problems at times. There's some hitches. Some of you have faced it. We have tried to resolve it as soon as possible. If you have not been up to your expectations, we apologize for that. We'll try to do it better next time. Tu, maybe you can say a few words. We can't hear you. Your voice.
I think you're muted.
You're muted. Yes.
Thank you for everyone to join with us, and hope you enjoy our first MOOC. We try to improve in the next time. Next MOOC.
CK?
Yeah, I'll just say thank you very much for participating. It's been wonderful. All this discussion actually, I think it taught us too, a lot of things. It shows different perspective. Different countries have different challenges. It's very interesting to all these things. Thank you very much.
Thank you, CK. Dr. Alfata?
Thank you, Dr. Brahms. Yeah, same as others. So I just would like to say thank you very much for joining this course. I hope you enjoy, and I hope it's beneficial for all of us. So I also learned a lot from all of you, particularly for practicing architects. So since I not so many involved in real projects, so I really enjoy the discussion. I think we have some unanswered questions, so maybe we can go better in the next MOOC. Thank you very much. That's all, Dr. Brahms.
Thank you, Dr. Pereira. Ren?
I'll start by thanking everybody for taking this on. I think main thing is it has been able to generate food for thought. I think as Mona mentioned, I think, and also like Tanvi, where food for thought, and then that will help us go forward. So I think that is a great advantage here, and hope and pray that everybody keep safe and keep learning. Thanks a lot.
Thank you, Dr. Pereira. Dr. Atalage, Rahula would like to say something?
Yeah, thank you. Thank you firstly for taking the leadership in getting it the program to realization, and all the colleagues who have contributed, sharing their knowledge, experience with their projects and so on. Of course, not forgetting the participants for their, thought-provoking questions and also sharing their experience. I hope we can take this to the next level in our next program of MOOCs, and all the best, and stay safe. Thank you once again.
Thank you. Thank you. And I would just like to mention that it was a real team efforts. All of us are, busy in our own activities, but we volunteer to work together to come up with this type of MOOC, because our objective is to reach out to as many young people as possible, to create an understanding and awareness, so that when you build, you will be building the future, so you can integrate these ideas and come up with a future which is much brighter for you and for the generation to come. So in this regard, we would like to thank you for taking the time to participate in this MOOC. And you have our email address. Anytime if you have any suggestions, questions, don't hesitate to write to us. We'll try to respond to you in whatever manner we can. Thank you very much. Wishing you a very nice evening and a good Sunday tomorrow.